Imagine your app suddenly explodes in popularity. Millions of users are refreshing feeds, uploading photos, logging events, and hitting your database every second. At first, everything feels great until your single database server starts choking under the pressure. Queries slow down, timeouts appear, then the server crashes and your entire app disappears with it. That is the exact problem Apache Cassandra was built to solve. Instead of relying on one giant machine, Cassandra spreads data across many ordinary servers called nodes. Those nodes form a logical ring, and every node is equal. There is no master server, no primary database, and no central boss making decisions. Any node can accept requests from your application. That design matters because it removes the biggest weakness of traditional systems, the single point of failure. If one machine dies, the cluster keeps running. So how does Cassandra know where data belongs? Every record has something called a partition key. Maybe it is a user ID, an order number, or a device identifier. Cassandra takes that key and runs it through a hash function. The result is a number called a token. That token maps to a position on the ring, and Cassandra instantly knows which nodes should store the data. But Cassandra doesn't trust a single machine with anything important. It stores multiple copies called replicas. If your replication factor is 3, every piece of data lives on 3 different nodes. Now imagine one node suddenly fails. Maybe the disk dies, maybe the machine loses power, maybe an entire rack disappears. Cassandra keeps serving requests because the other replicas still exist. When the failed node returns, Cassandra synchronizes the missing data in the background. That explains reliability. Now, let's look at speed. Cassandra became famous because it can absorb massive floods of writes without collapsing. The reason is its write path. When a write arrives, Cassandra appends it to a file on disk called the commit log. At the same time, it stores the data in memory inside a structure called the mem table. Then, the write is finished. Cassandra doesn't immediately search the disk for old rows and overwrite them. Later, when the mem table fills up, Cassandra flushes it to disk as an immutable file called an SS table. Immutable means the file is never edited again. New writes create new SS tables instead of modifying old ones. Over time, Cassandra merges and cleans these files through a background process called compaction. This design is incredibly fast because appending data sequentially is one of the fastest operations a disk can perform. Cassandra avoids expensive random updates and turns writes into simple append operations. There's a trade-off, though, and Cassandra is honest about it. Because data is replicated across multiple machines, replicas can briefly disagree. One node might have newer information than another for a short period. Cassandra lets you choose how much consistency you want for each query. Consistency level 1 asks only one replica for data. That's extremely fast, but can occasionally return stale information. QUORUM waits for a majority of replicas to agree before responding. That adds latency, but it gives stronger consistency guarantees. Cassandra also changes how you think about schema design. In relational databases, you normalize data and join tables together later. Cassandra avoids joins entirely because joins across many machines become painfully expensive at huge scale. Instead, you design tables around your queries. If 2 queries need different layouts, you often store the same data twice in different shapes. Storage is cheap. Slow distributed joins are not. This is why Cassandra shines in workloads with endless streams of writes. Sensor telemetry, click tracking, activity feeds, messaging systems, ride tracking, and time series data all fit naturally. Companies like Netflix, Uber, and Apple use Cassandra because they need systems that keep accepting writes even during failures. But Cassandra is not the perfect database for every problem. If your application depends on complex transactions, flexible joins, or rich relational queries, a traditional SQL database is often the better choice. Cassandra wins when scale, uptime, and relentless write throughput matter most. And when you need more capacity, you don't buy a bigger server, you simply add another node to the ring. That is the core idea behind Cassandra. Many equal machines, replicated data, lightning-fast writes, and a database designed to stay online no matter what fails.